and for the invitation to give this seminar or webinar. I'm terribly sorry that I cannot share my webcam. It seems that it's not working. So I don't know if it died during the last update of Windows. I'm sorry for that. Along this talk, I will talk about two-dimensional materials for optoelectronics, and I try to make like a compilation, a summary of all the past results that we have in the group in this topic in a way that is more state of the art, let's say, for the students, that just like showing like some of the latest results and so on. So I will try to motivate why two-dimensional materials are good for optoelectronics and what is the kind of like devices we fabricate and why they're useful. So I work since 2017 in the Material Science Institute of Madrid, that is part of the Spanish National Research Council. Okay, so it's like a national lab in the US or CNRS in France. So we have institutes around Spain, like each of these institutes on a topic, and this one is the material science one that is located in Madrid. So we are in the central part of Spain, but we are not in the centrum of Madrid. So we are not in the city center, we are in the outskirts, in the north part, which is okay because Madrid is a very lively city. We have nowadays almost everything is very lively city to spend your days there. So we are far away from the distractions. And now with the global warming and climate change, we even have like real snow during the winter. So Madrid now has everything, right? In this Material Science Institute, I am part of this 2D Foundry group. We are a research team with different PIs that we have common interest in two-dimensional materials, but we have different alternative approaches that we are complementary. For example, we have Professor García Hernández, that is the head of the Magnetism and Magnetotransport Lab. Carmen Munuera is the head of the Local Probe Microscopy Lab. And Beatriz Juárez is the head of the Semiconductor Nanoparticles Lab. And I am this person here, sorry. So as you cannot see me, so this is me. So I'm the head of the two-dimensional materials and devices lab. And we are still a small research team, despite of being a cluster of 4 PIs, but we are getting inertia little by little. So this is a gathering of the Scanning Probe Microscopy Lab and this material science, this two-dimensional materials and devices lab all together. All right, so let's start talking about why these two-dimensional materials for optoelectronics, okay? And the, let's say, practical motivation is that if you take a look to the responsivity of as a function of the wavelength of photodetectors, that they are commercially available and fully optimized, like silicon, germanium, or indium gallium arsenide, you will get a plot like this. So take into account the responsivity, amps per watt, is the theory of merit that tells you how sensitive it is a photodetector to light. Okay, so then we have like these values here. If we compare now with other two-dimensional semiconducting materials, right? So like these are conventional three-dimensional semiconductors, and these are two-dimensional semiconducting materials. You see that there is a huge difference in the responsivity of these materials. At this point, you have to notice that two-dimensional semiconductors, they are much better than, for example, graphene for photodetectors, because graphene has almost zero band gap, okay, or let's say, or a zero band gap. So it's a bad metal. It's not a semiconducting material. It means that it has a large off current and a large dark current. So even under dark conditions, graphene has a large current flowing through the channel. So which makes it really bad for photodetectors because of the lowest detectivity and also the largest power consumption. So semiconducting two-dimensional materials are preferred for optoelectronics. Okay, so now let's talk about molybdenum disulfide for photodetectors. Molybdenum disulfide is probably the first layered semiconducting material that has been isolated by exfoliation. So it's very similar to graphite and can be cleaved very easily, as you can see here. And it has an intrinsic band gap. Okay, and this is by far the most studied two-dimensional semiconducting material. Okay. With this molybdenum disulfide, you can easily fabricate a photodetector by placing this molybdenum disulfide in between a drain and source electrodes, okay, making a semiconducting channel. Okay, if you fabricate this on top of a dielectric and a heavily doped silicon backgate, then you can have a photodetector geometry with a phototransistor geometry. Then in this kind of device, the semiconducting channel is fully exposed, for example, to light. So you can easily illuminate your semiconducting channel here. Okay, since 2012, 2013, there were plenty of works already studying molybdenum disulfide for photodetectors. Okay, and you can see in this plot here from Andraski's group that the responsivity reaches 1000. Okay, so remember that we already discussed that in silicon, indium gallium arsenide, we are, let's say, about 1 amp per watt or less. And in this case here, we reach up to 1000 amps. So this motivated the community a lot, okay, to start studying these two-dimensional materials for photodetectors. But as I have to stress, up to now, most of the research groups, they still work on molybdenum disulfide or cousins of molybdenum disulfide, transition metal dichalcogenides, basically. Why these two-dimensional semiconducting materials have this huge responsivity? There are many reasons. So one is that these materials, they have a density of states that has discrete jumps. So you have some resonances. Okay, so this is standard for any two-dimensional material. Instead of having a continuous density of states, you will have a stepwise density of states. These transition metal dichalcogenides, they have a huge exciton binding energy. So they have a strong light matter interaction. But probably one of the main reasons why these materials, they have this large responsivity is because as they are two-dimensional materials, they are very sensitive to trap states, and therefore they are eligible to present a mechanism of photocurrent generation that is called photogating. Okay, I'm going to briefly explain what is this photogating mechanism. That is basically a particular case of photoconductive effect. In photoconductive effect, you will illuminate the semiconducting channel with photons that they have higher energy than the bandgap. And then you will generate an electron hole pair. Okay, and by applying a bias difference between the two electrodes, basically you will separate these two charge carriers. Okay, so you will generate 1 electron, 1 hole per photon. That will be the normal photoconductive effect. Okay, now in the case of photogating, as these two-dimensional materials, they have this sensitivity to trap charges because they are all surface, so they are really close to the traps that they are at the interface. So you can have these states here that they can trap the minority charge carriers. In this case, in the case of molybdenum disulfide, there is an N-type semiconducting material. You can easily trap holes, okay? And once you trap this hole, this electron feels the drift because of the bias difference that you have between the electrodes. So basically it will jump here to the drain electrode, okay? Once this electron is in this electrode, the channel is charged with a positive charge, okay? And Kirchhoff rules, they tell us that it cannot be charged. You're applying a voltage difference, so it cannot be charge accumulation, okay? Therefore, what the semiconductor does is it steals 1 electron from the source electrode in order to keep neutrality, okay? But this electron again feels the bias difference and then drifts towards the source. And this process can take many times, okay? And you can accumulate a lot of electrons in the source, sorry, in the drain, okay, until this hole gets detrapped, okay? Therefore, basically, this photogating mechanism has a gain. So you generate plenty of electrons per photon. And basically, this gain can be given by a ratio between the detrapping time, so the time this hole can live in this trap, divided by the drift time, the time it takes 1 electron to jump and go to the other electrode. Okay, usually there are several orders of magnitude between these two times. Therefore, you get like thousands of electrons per photon. Okay, that explains why these two-dimensional materials, they have 1000 amps per watt. Okay, fine. Now, I mean, this is like the state of the art. Okay, so most of the people, they keep studying molybdenum disulfide for optoelectronics, and I have to motivate you why to make the effort of going beyond that. Okay, and there are several technical issues on molybdenum disulfide. One of the ones that I want to highlight is that it has a limited spectral bandwidth. Okay, when I mean bandwidth here is a spectral bandwidth. Okay, so basically these photodetectors, they are blind for photons that they are beyond 680 nanometers. So they cannot detect anything in the near infrared. Okay, and also because of this photogating mechanism, okay, so one important thing here that I didn't stress is that, okay, so you get the, so if this detrapping time is long, you get a large gain, but then the response speed of your photodetector is very low, is very slow, okay, because basically the speed is limited by this detrapping time. And that is exactly what happens in molybdenum disulfide. You get 1000 amps per watt, but then if you switch on the light, it takes like, 30, 50 seconds to react to light. If you switch off the light, it takes like almost 100 seconds to react to light. Basically, you can fabricate, for example, a very sensitive photodetector, but if you want to use it for surveillance applications, for example, a surveillance camera, you are going to get robbed and nobody's going to see it because it's going to be very slow. Okay, so if we put all this together, so molybdenum disulfide has this ultra high photo response that is cool, but it has this spectral bandwidth that is narrow. Also, molybdenum disulfide is basically a direct bandgap semiconductor only when it's a single layer. So that limits the optical absorption that you can have in this material. And it's very slow because of all this photogating effect. And moreover, molybdenum disulfide has an intrinsic N-type doping. For example, you might be interested in making PN junctions, for example, to build up a solar cell. This cannot be done with molybdenum disulfide itself. So you have to play tricks. Okay. So back in 2014, basically the panorama was like this. I mean, like people were using graphene, molybdenum disulfide, and hexagonal boron nitride. So like let's say a metal, a semiconductor, and an insulator, and there was nothing else. Okay. But if you take a look to like three-dimensional semiconducting materials, you see that basically these material scientists have been filling all the gaps in the electromagnetic spectrum. Is very important because for each application, you have just a window of wavelengths in where you optimize the material. So if you want to do thermoelectrics, then you will go to this family with lead, for example, lead selenide, lead sulfide, or indium arsenide. Okay, if you want to do some photovoltaics, then you have basically this window here that optimizes. So silicon is slightly out of the window that optimizes photovoltaics, but it's close enough. Okay, so there is a take-home message. Now, in the case of two-dimensional materials, there were plenty of gaps. And one thing that we should stress is that fundamental physics advances when you explore new materials, because usually you find out new phenomena that you were not expecting. And also sometimes some new applications comes hand by hand with new materials that you didn't explore so far. So that's why I believe for students is very important to keep an eye open in spending a little bit of their time in developing new materials, isolating and characterizing new materials. So I'm going to talk about few other two-dimensional semiconducting materials. Some of them they're still quite unknown, let's say. They are not heavily studied so far. Black phosphorus, for example, is nowadays more and more studied, but still far behind this molybdenum disulfide. Still nowadays, these three families of materials, they're understudied if you compare with transition metal dicalcogenides. Okay, and these three materials, they fill some gaps in this electromagnetic spectrum. Okay, but of course, there's still plenty of things to do in in the rest of the electromagnetic spectrum. So let's start talking about indium selenide. So you have to notice that there are two different indium selenides depending on the stoichiometry. So this is indium 2, selenium 3. But there is another layer semiconducting material, that is indium-1, selenium-1. Okay, so today I'm going to talk about this indium-2, selenium-3. And what I find interesting about this material is there is a photodetector with a gate tunable detection mechanism, and it has a huge bandgap range tunability depending on the thickness. Okay, so this material can be exfoliated similarly to molybdenum disulfide, graphene, etc., in shape of flakes, and then you can do your microfabrication to put electrodes, and you can do your field effect transistor characteristics. And one of the things that you've noticed first is that this material gets decent enough mobilities, 30 centimeters square volt per second. And usually we perform these kind of measurements in 2-terminal configuration. So, well, 3-terminal configuration with the gate. So, which means that we are underestimating the mobility because of the contact resistance. Okay, so these values here, they're quite good, let's say, in comparison with moly disulfide. So at room temperature in moly disulfide, we get like something between 0.1 and 10 centimeters square volt per second. Now, this material has this N-type doping. Okay, so for negative gate voltages, the current is negligible, is in the off state. And when you start applying positive gate voltages, then you start turning on the semiconducting channel. So you start populating with more and more and more electrons. And what we see is that basically this responsivity can be tuned from being generated by the photoconductive effect to the photogating effect. Okay, in the photogating effect, you get this very steep slope and very large values. In the photoconductive effect, so if it will be like pure photoconductive, we will expect a flat line here and basically reaching to 10 to the 0 amps per watt. Okay, that will be pure photoconductive. So still here, there is a little bit of photogating. But also you can see this tunability of the photoconductive mechanism, because if you are in positive gate voltages, it takes a lot of seconds to switch off the semiconducting, this photodetector. Okay, so you switch on the light, it takes some seconds, switch off the light, and it takes like several tens of seconds. Okay, so these are seconds. If you go now to negative gate voltages and you repeat this experiment, then this speed is much faster. Okay, and now these numbers here, they are milliseconds. Okay, so because this is in the photoconductive effect, now you are not limited by this detrapping time. So you can indeed tune from a semiconducting photodetector that is very sensitive but slow to something that is rather insensitive in comparison, but much faster. And you can stop at any point in between. Okay, so by applying a gate voltage, you could easily decide which kind of like a trade-off between responsivity and response speed you want to have. Moreover, one of the things that makes interesting this material is that if you study the absorption spectrum, you see that the absorption band edge changes in energy a lot between flakes that they are very thin to flakes that they are getting thicker and thicker. So thin flakes, they have pretty large absorption band edge energies, so large band gaps. And as you make this material thinner and thinner, the band gap becomes smaller and smaller. So basically, so you can tune all the way from 1.4 to 2.8, so it's a huge tunability. And basically the physics underneath it is similar to these bells. So it's quantum confinement, basically. So you are confining the electrons in a smaller and smaller space. And then the energy levels, they split apart. So similar to a small bell. In a small bell, you have a high frequency, ding, right? So because these sound waves are confined in a smaller space, if you go to large bell, boom, the frequency is lower energy, because the sound waves, they are confined in a larger space. And same thing happens here. So you can tune this band gap of the semiconducting material by just changing the thickness. Okay, and that makes indium selenide particularly interesting if you compare with other layer semiconducting materials. So basically only black phosphorus has a certain level of similar tunability. The rest of the semiconducting material, so this is like the band gap range as a function of the thickness for different layer compounds. And you see that how indium selenide has a huge band gap selectivity here, compatible with this comparable with the one you have in black phosphorus. And other materials, they have a much smaller range of band gaps as a function of the thickness. Okay, so this allows you to cover a wide range of the spectrum. The next material I want to briefly introduce is titanium trisulfide, because basically this titanium trisulfide opens up a brand new family, the transition metal trichalcogenides. Okay, so everyone in this optoelectronics, 2D optoelectronics, are familiar with moly disulfide and transition metal dichalcogenides, but in this case, this is trichalcogenides. So this is, let's say, a family as large as the dichalcogenides, but it's rather unexplored so far. And what makes these materials different from the dichalcogenides is that they have a strong in-plane anisotropy. So this makes this material to grow in this kind of like platelets. They are more like a ribbon shape, okay, but they can be exfoliated. So they have a layered structure. These materials are grown by Isabel Jimenez Ferrer in the Autónoma University, nearby to my institute. And to motivate you a little bit, so this titanium trisulfide, that is the first trichalcogenide isolated by mechanical exfoliation. So like if you take a look to the citations per year, until 2014, there was almost nothing. Okay, so this material has been studied from the late 70s, but it was kind of like, just anecdotic, let's say, research. Now is getting higher and higher. So it's getting a lot of inertia. Okay. And as I said, so this material makes this kind of like layered structure, okay? But if you take a look more carefully to the structure, not the 3D, but this simplified structure, you get these things generate chains of titanium trisulfide that they go out of the screen. And these chains interact with each other by these sulfur titanium bonds here. So basically you have one chain, another chain, another chain, another chain, and then you have these interchange bonds here. And that makes the layer. And then the layers interact to each other by just van der Waals forces. Okay, because basically you don't have any dangling bond here. And therefore you just interact by van der Waals forces, making these stacks. So regarding these anisotropic properties of this titanium trisulfide, one of the easier things that you can do in the lab is you can just take one of these flakes exfoliated by mechanical exfoliation, put it on a transparent substrate, and start taking pictures in transmission mode in an optical microscope. And if you use a linear polarizer underneath and you start rotating the linear polarizer, you see how the transmittance of this titanium trisulfide changes with the alignment of the linear polarization angle with the crystal direction of the flake. So this is the elongated direction of these flakes is the B axis of the crystal. And when the light is polarized parallel to the B axis, the flake becomes dark. So it's very opaque. When the light is perpendicular to the B axis, it's much more transparent. So this is similar to a metal wire polarizer. So basically when you're polarized along the B axis is the direction in where the resistance, electrical resistance is lower in titanium trisulfide. So basically you can excite electrons going back and forth, back and forth, back and forth, back and forth. So basically you can quench the electromagnetic field. In this direction, the electrical resistivity is much larger. Therefore, it is much more difficult to excite electromagnetic waves in this direction. So now we can actually measure this anisotropy in the electrical properties of the material. So we can take one of these flakes fabricated by mechanical exfoliation, and we can pattern electrodes at different angles. So we can measure between this and this, between this and this, between this and this, between this and this, in order to get information about the angular difference in the electrical properties. And then we have here mobility plot in polar plot, and we get much larger mobility along the B axis than the A axis. Okay, we get mobilities up to 80 centimeters watt per second, which is huge. Okay, and then it makes sense because, as I said, so when the light is polarized along the B axis, the flake absorbs much more light because it's the low resistance or high mobility axis here. Nicely enough, this material presents large enough responsivities in a broad range of the spectral spectrum of the spectral range, sorry. So like up to 1000 nanometers, basically, and is fast enough. So it has a good trade-off between all the different parameters, okay? So because it has photogating, but the detrapping time is fast enough, and it has a narrower bandgap than molybdenum disulfide. Maybe the only drawback of this titanium trisulfide is that it's an N-type semiconducting material, a strongly N-type. So it's difficult to use it for a PN junction, for example, if you want to fabricate a diode, a solar cell, or if you want to make some logics. Now, the next material will be black phosphorus. There is one of the examples of an ambipolar semiconducting material with a narrow, very, very narrow gap. Okay, black phosphorus was discovered in 1914, just by serendipity. So Bridgman was trying to modify white phosphorus to change it into red phosphorus by applying temperature and pressure. And then what he discovered was some black stuff there, like dirt stuff. But he was smart enough to not just throw it away and try, other things. So he said, maybe, these black crystallites, they're interesting. So one important thing is that serendipity requires to be, eyes wide open. Okay, so if you don't have your eyes wide open, so you can have a serendipity discovery and not just pay attention to it. Okay, since 1914, almost nothing happens until the 50s. In the 50s, Case was studying the electrical properties of bulk. And then basically nothing happened until 2013, where Joan Bossan gave a talk in the March meeting. And then all this field of black phosphorus started. And one of the things I want to stress is that up to 2013, so it was thought that graphene was the only single element two-dimensional material. Okay, because it was, so from 2004, plenty of people isolated other two-dimensional materials, but all of them, they were compounds: moly disulfide, niobium diselenide, high temperature, so this BS, CCO, mica, all different compounds that they have complex chemical structures. And black phosphorus is the first single element two-dimensional material beyond graphene that was isolated and opened the door to more mono-element two-dimensional materials. And again, since 2014, so basically Joan Bossan talk was in 2013, the first papers came out in 2014, and the field is growing like hell. So it's one of these research fields that is very active. So what makes different black phosphorus from moly disulfide and titanium trisulfide and indium selenide is that it's ambipolar material. So if you make a field effect transistor and you apply negative gate voltages, you get large Hall current. Then when you start applying more and more positive gate voltage, this Hall current gets decreased. Okay, so you're depleting the channel. At this point, you reach the off state of the channel. And if you apply more and more and more positive gate voltages, you can start having electron conduction. Okay, in this particular case of the device here, we have a large asymmetry of the mobility between holes and electrons. So it conducts much better holes than electrons. By choosing right electrode materials, you can actually get a much more ambipolar material. For example, if you use aluminum instead of titanium gold. Okay, as a photodetector, this material is very nice because you can get responsivity both in the electron and the hole regime. And in bulk, when you have a multi-layer of black phosphorus, the band gap is around 0.35 electron volts, so very narrow band gap. So it means that you can go all the way to near infrared and even beyond and still having a response there. So regarding the responsivity, the device is not that highly responsive, okay, but it's much faster than many other devices that we studied so far. So it has this thing, but for sure, the best thing about black phosphorus is that it's ambipolar. So within the same material, you can create a P and an N semiconducting material. You can exploit this ambipolarity in order to build up, for example, a solar cell. So you could start, fabricating a pair of gold electrodes. So this is a cross section, okay, of this device here. So these are optical images, and this is a cartoon showing the cross section of the sample. So we will have our pair of electrodes here. Now, by using deterministic transfer, we can transfer hexagonal boron nitride flake here. This hexagonal boron nitride is an insulator material. Okay, so we transfer this boron nitride on top of the electrodes. Then we transfer a black phosphorus flake here on top of the electrodes. Okay, but is disconnected by the hexagonal boron nitride. Okay, so this works as a dielectric here. And now we can go to the fabrication room again and put a pair of electrodes here. Okay, drain source electrodes. So now we have basically like this region here, we have this left gate and right gate here, and we can control the doping level individually on these two regions of the space. So we can actually like play tricks like if we apply positive gate voltages, then we have an NN configuration. Okay, so in both devices, and then we have no rectification or very slightly rectification. If we apply negative, so we are in the PP, so conducting with holes, okay, and now we get a very straight line. Remember that it conducts much better for holes than electrons, so that's why we have this such a steep line here. If we apply negative and positive, then we can get P, N region, right? And then we get rectification diode-like behavior like this one here, okay? Now, we can put this device in this configuration, PN, and we can illuminate just the junction between this P and N. And when we illuminate the junction, we create an electron hole right here at the junction. And this electron and hole, they feel this built-in potential that we have here. So basically they get separated, even without applying any voltage. So basically we are creating a tiny solar cell out of this black phosphorus. And indeed, if you study the current versus voltage characteristics of the device as a function of illumination with higher and higher and higher power, you see that you start first with this rectification curve here, and you start generating current even at zero bias. Okay, so this can be used for energy harvesting, and it can be even used in the near infrared because black phosphorus is sensitive to wavelengths in the near infrared and even to the short wavelength infrared regime. So like it reacts to light up to 3.2 microns, if I remember correctly. Disadvantage of black phosphorus is that it's very temperamental regarding the environmental exposure. So if you expose this black phosphorus to air, it's highly hygroscopic, and the reaction with the oxygen dissolving water tends to degrade the black phosphorus. So you need to work out different ways in order to encapsulate it or to work in vacuum all the time and so on, right? So this is the thing that is basically the drawback of black phosphorus. So this will be the summary of these three semiconducting materials that we studied, right? And with the pros and the cons of the different materials. But the most important message, apart from like all these, like blue and red points here, is that there is not such a thing as the killer material. Okay, so every different application requires a different material. Okay, so then we need to have a broad catalog of materials, as broad as possible, to be able of finding the right material for the right application. Okay, so even, I mean, you could say, okay, no, titanium trisulfide is the best one. No, it's not the best one because, for example, it's not ambipolar, and black phosphorus is ambipolar, but black phosphorus degrades, so you have to have as broad catalog as possible to find the material that optimize your application. And at this point, so we can start putting all this in context. Okay, so there are plenty of works, like in the literature, studying two-dimensional semiconducting materials, but as I stressed, most of them, they are dichalcogenides. Okay, most of them, they're dichalcogenides. So that's why I wanted you to stress on these different materials in order to, like open up a little bit your mind. Okay, now this will be the context of what we got so far, but the challenges is to get fastest devices with high gain, because it is very simple to get higher gain, but increasing the photo gating effect. Okay, that is very easy, but then the devices become slower. So this way is very simple. this way is very challenging, and that is what is still an open challenge for you guys to solve it out. Now, I want to give you a bonus track, so about some slightly different material, okay, that you can do optoelectronics with. And this material is kind of funky because it's called Franckeite. It's a mineral, it's a natural mineral. And what makes it very different from the other materials have been studied so far is the fact that this is naturally, it becomes this superlattice structure. So basically you have thin disulfide here, antimony monosulfide here, thin disulfide, antimony monosulfide. Okay, so with hexagonal, tetragonal, orthorhombic, hexagonal, orthorhombic structure. Okay, so this is like this structure of this lead monosulfide basically, and this it's found in nature in this Franckeite mineral that was discovered by the Francke brothers, so Carl and Ernest. So that's why it's called Franckeite in 1893. So these two gentlemen, they were engineers. I think they were looking for oil in South America, but they were, they were working for one of these oil companies in South America, but they were as a hobbyist. So they were collecting minerals. Okay, so then they found out this new mineral, and they gave the name of Franckeite to it, and is completely unexplored material. Okay, so if you take a look to the number of papers published in the last century, it's just like 200 of papers or something like that. Okay, so it is very exciting to work in this kind of like unknown materials. So I'm a mineral collector, and I happen to have Franckeite mineral in my collection. So I told one of my colleagues, Adai Molina Mendoza, why we don't try to exfoliate it actually. So the structure of this material, this superlattice structure of this material was actually known already because of the works of TM. So they were works on transmission electron microscopy in the 80s, okay, 1980s. And it was known that it has this structure. So we said, okay, so it has this structure, maybe we can exfoliate. I mean, it looks like a layered compound, right? So it looks like a Van der Waals material. Let's try to exfoliate it. But the rock looks like this, as ugly as this. I mean, nothing to do with graphite, nothing to do with molybdenite, so really ugly. But when you just zoom in, you take a microscope and you zoom in, you see that indeed the surface makes these kind of long terraces. Okay, so it means that, okay, so with this kind of a structure, one can think of exfoliating the material. Okay, so it's not crazy exfoliating this. So we started to exfoliate this Franckeite. And one of the first things that we did, it was trying to reproduce these TM studies from the 80s. So we transferred this Franckeite on TM grids. And what we saw is this characteristic ripple pattern that happens in Franckeite. And when you do diffraction electron studies, so you see that you can resolve in these H and Q lattices, that they are these H and Q lattices here. So you can indeed resolve it. And these points here, they're sharp enough that is telling you that these layers, they're really well-oriented layers. So it's not like they are randomly oriented. So they are really stuck in a particular order. And we see this wavy pattern that has been reported already in the TM studies. And I will come later to this because this is actually not well understood completely. Okay, so this is a moire pattern, but it's not a trivial moire. So our friends, Juanjo Palacios did some calculations on DFT calculations, and this material has a narrow gap. And interestingly, the electrons and holes, they get separated in the space. So it's a type 2 sort of superlattice, where holes, they live in these H layers and electrons, they live in these Q layers. Okay, so that makes interesting, for example, in order to do time resolve spectroscopy, optical spectroscopy studies. And in collaboration with Emilio Perez in India, so we fabricated these inks, these suspensions of Franckeite platelets, and we study absorbance, and we saw that it absorbs under 0.5 electron volts. Okay, so it has this exciton peak over here, so which is telling us that it's indeed a very narrow bandgap semiconducting material. And this is a flake of Franckeite, just few unit cells. So like this is like 5 unit cells thick, 5 or 4. And we have this flake transfer in between 2 gold electrodes, okay, in order to fabricate a photodetector. And the device is rather stable. So you measure the device, and after 40 days in air, so you have just a small drop in the current. It's a P-type semiconducting material because the current decreases when you increase the gate voltage. Okay, and it reacts to light all the way to the near infrared. So 940 nanometers, it was the longest wavelength we had back then when we studied this. So we have a stable P-type narrow bandgap semiconducting material. So this is an excellent alternative to black phosphorus if we want to fabricate, for example, heterostructures between M-type and P-type materials. So now we can take a single layer molybdenum that is an N-type semiconducting material. We can transfer it, and we can transfer a Franckeite flake on top. So now we have here a PN junction, basically, right at the junction. And indeed, this device has a rectifying behavior, and it can be controlled. The rectification ratio can be controlled basically with the gate voltage. And as Franckeite can absorb light in the infrared, so this has photovoltaic effect even in the infrared. Surprisingly enough, Franckeite is an anisotropic material. Okay, so basically you have a square lattice and a triangular lattice. Okay, making this super lattice. Okay, so one on top of each other. So if you just take your Illustrator or Inkscape, wherever, and you plot this square lattice and a triangular lattice, and you put them on top of each other, you will see that you cannot explain an anisotropy in plane because both lattices are isotropic. Okay, but surprisingly enough, if you fabricate devices with this Franckeite flake with electrodes on different angles, and you measure the conductance along different directions, you see that the conductance fluctuates. And also the transmittance of these flakes also fluctuates. Okay, so with the angle. And they are aligned both axes. Okay, so this is the absorbance. So the absorbance gets larger along the longest, along the highest electrical conductance direction, very similar to what we have seen in titanium trisulfide. And if we do TM in the same flake, we see that this direction actually is parallel to these ripples that we saw. What happens is that even though these layers, they interact to each other with van der Waals forces that they are weak, these interlayer forces, they are strong enough to slightly deform the lattices according to this moire pattern in order to minimize the addition forces between the lattices. Okay, and therefore you get some strain pattern following these moire directions. And this strain pattern is the one changing the electrical conductivity. And because of the anisotropy in the electrical conductivity, you get an anisotropy in the transmittance. So to finish with this Franckeite, this bonus track. So Franckeite is a natural van der Waals heterostructure or superlattice. Okay, so it's a very simple way to fabricate a superlattice by just mechanical exfoliation, and it's a good alternative for black phosphorus because it has a narrow bandgap, is P-type, but is air stable. And as an example of what I told you about, like what happened when you explore new unexplored materials, is that we find out something we didn't expect. We didn't expect to see an in-plane anisotropy, and we find out that just this weak interaction between these layers is strong enough to modify locally the position of the atoms and induce this in-plane anisotropy. And now I'm going to give you just a teaser of something for students I'd like. Okay, so it's some new field of research we are working in the lab in the last year and a half. So we are working on fabricating optoelectronics and electronic devices on paper, integrating two-dimensional materials in order to fabricate low-cost, low-tech, and biodegradable devices. So basically, we are integrating different van der Waals materials on paper substrates, but just a dry process is directly rubbing So you can buy powder of tungsten disulfide and you can rub it with a cotton swab. Okay, you will see now. And it creates a film of tungsten disulfide on the surface of paper. And then you can use graphite pencil in order to put electrodes to it. Okay, like this here. So it's a very simple way of fabricating photodetectors with your van der Waals materials. Okay, and just to show you an example of what you can do with this, so we build up some photodetector with moly disulfide on paper, and we build up a very simple single pixel camera setup. Is basically a laboratory version of a scanner, okay? And then we took this smiley face here, and we took actually a picture of this smiley face using our paper-supported photodetector as our pixel in our camera. You can see the result here, okay? And with that, I will just to acknowledge the funding sources, the Ministry of Science and Education, the CSIC, the European Research Council, and the Distinguished Science Fellowship Program of the King's Out University. And thank you for your attention. Thanks.
Thank you, Professor Castellanos-Gomez, for the beautiful talk. So I have one question regarding the Franckeite crystal. Can you hear me?
Yes, yes.
So did you transfer this Franckeite flake with dry transfer technique, or did you use some other transfer techniques?
So we use the dry transfer technique for that. Yeah, PDMS. Sorry.
Okay.
This one here. We use PDMS transfer technique, yes.
Without any carrier polymer?
No, no.
Okay.
Can I ask the Mahatma?
Yeah, sure.
Thanks, Andreas, for a wonderful talk. Always something new to learn, and you are known for making devices which are accessible to common public as well, coming in future. I have some questions. One question I have is about TIS3, where you showed that it's quite fast. It also has large responsivity, right, in photogating.
Yeah.
But does it fit together there? I mean, compared to MOS2, as in the responsivity is large, but it's fast because the mobility is larger than MOS2, or what's the reason?
That is exactly the reason. Mobility is larger and resistivity is lower than moly disulfide. So the drifting time is much smaller in titanium trisulfide. So you can get similar gain with lower trapping time.
I see. And responsivity of MOS2 based transistors, how much is it compared to this number, like compared to 1000?
Oh, it's basically also 1000. I don't remember if it's for the same power. I don't remember if it's for the same power density. So it might be that here we have lower power density actually. So it might happen there.
So I remember some numbers like 10⁻⁸ or 10⁻⁹. What were those? Can you remind me?
Sorry, 10 to the
10⁸.
Oh, yeah, but that is with the persistent photocurrent. No, yes, that is right. So, but that is one of the extreme cases of photogating in where you have response times of hours. Okay, and in that case, you can indeed build up photocurrent up to 10 to the crazy numbers. Yes, that's right.
Yeah. So there were those groups which were claiming that one can make memories with those transistors and so on.
It could. So the point is that this persistent photocurrent is something I don't usually discuss in the context of photodetectors because it's not useful for photodetectors, but it doesn't mean that it's useless. It is useful for photo memories. Correct.
I see. And what's the size of, rough size of TIS3 flakes which you get after exfoliation? You showed some plot, some I think it was SEM image or something, but I could not understand the scale bar. Yeah, this one.
Well, I think this scale bar is 100 microns deep. So
Okay, this one. Okay, I see.
Yeah.
So flakes are fairly large then for optical studies.
Yes. So for example, this is so like depending on the temperature you grow it, you can get different aspect ratios. Okay, so this has been grown at low temperature. So then it's basically similar in the two directions. Okay, so then this we call flakes, and the other ones we call ribbons, but they are usually like several microns width and very long usually. So like if you grow at high temperature and you make these ribbons, the ribbons, they can be like 100 microns long and maybe 4 or 5 microns wide.
I see.
Width.
That's quite good. And have you done polarization resolved absorption measurement on this? Because I was curious. I mean, what's the shifting of the band edge in terms of energy or wavelength when you go from one polarization to the other?
I don't remember if we have done that, because I think we installed our micro transmittance later.
I see.
Actually. So I think we studied just the transmittance with, red, green, and blue channel, from the pixel cameras, and we fabricated photodetectors and we use polarized light. But I think we have not carried out polarization result transmitting measurements. I think we have not. Because
this looked very interesting. One slide back. What was the channel here? It was red, green, or blue. I mean, it was one of the channels, or it was complete broadband?
No, this is complete broadband. So that's why it becomes like brownish.
Oh, this looks very interesting then. I mean, then the band edge shifts, it seems appreciably when changing the polarization.
No, I'm remembering now. So we have done these measurements. I think we have done these measurements, and we have calculated the refractive index and and extinction coefficient as a function of the polarization angle. And so we have one old paper about like birefringence and dichroism in titanium trisulfide. Yes.
I see. No, this is interesting because compared to, for example, RESE2 or RES2, there the band edge shifts only by a few tens of MeVs if one goes from one polarization to the other. It seems here the effect is much larger.
Yes.
Okay. Thanks, Andres.
Thank you.
Tamagna, where are you?
So, is there any other question for Professor Gomez from the audience? So if not, we thank Professor Andres for giving this excellent talk. We would like to have you here either in person after some days. Thank you, everyone.
Thank you so much.
Thanks, Andres.
Have a nice one. Bye-bye.
Bye.
Bye.